Alright, in this video we're going to revisit sets. So we haven't talked or used sets too much, but they're really also very powerful data structures. They are basically used when you don't need to keep track of any order in your data set. But instead just need to know whether or not an item is in your data set. So these are two really good pictures to contrast the two, and I'm contrasting maps and sets because under the hood, which I'll talk about in a second, they're implemented the same way, but they actually are two very different abstractions, which is interesting. So a map is used if you need to do quick lookup, right? So if you have a key and need to be able to look up a value, it's really powerful. It comes up all the time. Almost every time you can't think of a faster way to do something, a lot of times it's like, oh, it's a map. It's a hash map. A set, on the other hand, you can just think of as like a container that holds things, and you just want to know whether or not something is in there. So, if you wanted to make it analogous to like a bowl, like maybe you have like a whole bowl of candy and you don't really care like where the candy is or how to get to it or how many there are. All you care about is like, is there a piece of dark chocolate in that bowl? And like, that's all you care. You just want to know if it exists. That's the idea of a set. So as a result, because all you care about is whether or not something is there, it can't handle duplicates, just like you can't handle duplicate keys in a map. And there's no order to the data set. So there's, again, two ways to implement. The first way is with a binary search tree. In this case, there actually is order to your items, and so if you traversed your set, you would actually be able to traverse the items in a particular order, but the abstraction doesn't require any order. A set is used when you just want to be able to quickly determine whether something is or is not in the data set. And so there's basically two ways to do that. One is with a tree, and one is with a hash table, or two quick ways to do it. There's lots of other ways to implement it. And so with a binary search tree, it comes with it that you can iterate over the elements in sorted order if that is useful. On the other hand, the hash map, or the hash set, uses the hash table, and then when you iterate over the elements, there is no order to them because the hash function is, basically placing it randomly or in no particular order into the array. It's not random, but it appears random. So these are the two different ways. So what does this look like? So if we were to insert these items into a set, so in C++ it's called a set that uses a binary search tree, and we inserted in whatever order we wanted. Let's say we put in H first, and then we put in A, and then we put in B, and then we put in M, and then we put in K, A, B, C, D, E, F, G, H, I, J, K. So K goes this way. Okay, I'm going to take those arrows out. Let me do maybe one more. I'll do an N, so it goes here. And you keep going. The data is just stored in a tree. So then anytime you want to know, like, is there a K in my set, what you would do under the hood of contains, or whatever that function would be called, is you would just traverse the tree and check to see if you ever run into a K, and that's going to be a log n search. Now, what's going to be stored in the tree? Well, in this case, you only have to store the item itself in the tree, right? There's not another value to set into that node because a set abstraction doesn't have key value pairs, it just has a single value. So that's the general idea of a set. It's just a way to like organize the data in an efficient way so that when you need to put something in the set, or when you need to remove something from the set, or you need to look up if something is in the set, it's efficient. On the other hand, if you were to set up an unordered set, with a hash table, in this case, you would be hashing your key. So when you hash your key, what comes out is the index. And then the index is going to tell you, where to put your data. So in this case, let's say that our hash function for this particular I'm going to just write a quick hash function so that we could look at it. Let's just say it returns the character minus a. And so that way it'll make like lowercase a 0, lowercase b 1, lowercase c 2, etc. So if I go ahead and insert a into my unordered set, what it's going to do is it's going to put in a, and that's going to put out 0, so it's just going to put a here. If I put in C, C is going to put out 2, and then it will put C here. Sorry, that should have put A there. Right here. And etc. And so in this case, the hash table is only going to store the key itself, right? Because there would be no reason, or it would be unnecessary to store anything else with a set. Obviously, there's all sorts of different data structures and different abstractions you might want and need, but in the case of a set, you're assuming that you're just trying to know whether something is in or is not in the container. And so in this case, when you do lookup, you just go through the hash function again and see if something is in that array. So it's possible, if you can write a hash function that has no collisions using an unordered set, that you wouldn't even need to store really anything in your hash table. Instead, you could just store true and false values, right? So you could say this is true and this is true, and that everything else is false. And if there's no collisions, that would be enough information. That would be all you needed. But it's unlikely that you were setting up a hash function that had no collisions in a real problem. But if that's what you were doing, then there's not even a need to put the data in there, right? Because you don't need it. You might not need it. So this is sets. So I wanted to revisit this because sets are something that we haven't really needed to use in too many different scenarios. I've actually thought about using it in a lot of different projects that we've been working on, but we haven't. It's a really good thing to use if you want to avoid having duplicates in something, or you want to keep track of whether or not something has a duplicate. Obviously, a set is like a natural abstraction for that. And then it's really, really common in graph algorithms. So it'll come up a lot in the graph algorithms that we're working on, mainly because you set up these big networks of graphs, and a lot of times when you're traversing them, you don't want to revisit a node again. If you're searching for something, you wouldn't want to ever go back to the same node. So a set is a really good abstraction in order to keep track of where you've been without having to actually go back there. So that is it for revisiting sets. Thanks.